To the easy stuff. My name is Rainer Grimm. I'm software developer since, oh no, forget about it, 1999. But I started 2016 as an independent trainer, particular for C++ and a little bit also for Python. So that's all about me. Okay. Now let's start with the more interesting stuff. I want to talk about concepts. And you see it, it's an evolution or it's a revolution. You will see what is my perception. A first overview. This is just the topics I want to talk about. I will give a first overview. I will talk a little bit about history, but only a little bit. Then I talk about the boring stuff. But boring stuff is important because it's quite easy to make no mistake. Then more interesting stuff, such as the placeholder syntax, such as syntactic sugar, and, of course, we can define our own concepts. Let's dive in. First overview. First of all, pantarray. This means it's flowing. That means, in particular, the features may change a little bit, only the syntax in the nearest future, but it's nearly fixed, I assume. Okay, now a first overview. I want to start with some strange observation. In C++, in particular, we have functions which are too specific or functions which are too generic. Okay, you have a function. A function such as call it add. If you don't recognize or don't use function overloading, can only accept a specific type, such as int, float, double, and you know it. This means you have explicitly to define this function for each type, which is terrible. What did we do to overcome this issue? We have strange rules such as narrowing conversion. You can use a double to, instead of an int, for example, and it will, the part after the comma will be removed. Or we have rules such as numeric promotions. Have a look here. I can use a double to invoke a function which takes an int, which is terrible, but it's possible. This is one side effect of this. A function only works with one type. And we have rules such as promotions. I have here a bool which I can use to invoke a function which accepts an int. Is also possible. This is one wrong way from my perspective. And what is another wrong way? We have templates. We have function which could accept all types. And sometimes the types will not fit. Such as here, I have defined the GCD algorithm. It requires modular operations, such as here, and if I invoke it with a double, I get a terrible error message. Two wrong ways, too specific, too generic. And what's the solution? Of course, you know it, concepts. Concepts is the solution. Now we have something in between with semantic. Okay, what can we do with concepts? We can express the requirements to template parameters as part of the interface. Okay, this is fine. Concepts support the stuff they should support. Overloading, you can specialize partially full on class templates. It's quite natural. If you make something wrong, you will get a quite readable error message. So we got nice error messages. Then we have now a more general concept or idea of placeholders, not only auto, but also constrained placeholders such as concepts. Of course, you can define your own concepts, and you can use them for class templates, function templates, non-template members of class templates. Okay, before I dive into the details, one short detour, the long history. The first time I recognized concept, it was around 26 or 28. To be honest, I don't know it exactly. They reminded me, they are not Haskell type classes, but they reminded me to Haskell type classes. What are Haskell type classes? You see here part of Haskell's type classes hierarchy. They are as you see it, a hierarchy of types. And for to be specific, on the left, to support the type class ordering, you have to support the type class equal. It's a kind of inheritance hierarchy. This is Haskell's type classes system. I will come back to this picture in a few minutes, or maybe in half an hour, and try it out if I can implement part of this hierarchy in C++, meaning with concepts. Okay, this was my first impression, but it's wrong, it's something different, but this was my first impression. And the long way started or ended 29. In Frankfurt, I don't know why it always happens in Germany, concepts were removed from the C++ 11 standard. The reason you can read here, evolved into a monster of complexity. Okay. Then with 2017, there was the idea of getting concepts light. But now with 2020, we are done. Now we have concepts. Okay, this was only a little bit of history. You see, important feature sometimes take a long time. Okay, now to the boring stuff. Why is this boring? Because it behaves so natural. But this is not bad in case of programming something. Okay, here's the first concept which I use. In the first case, you see it here, I cannot point to it. Maybe I can use my mouse. In the first case, you see here, this is the, I would say, a requires clause. Here I specify for the algorithm sort that cont should support the concept of sortable. I assume you know what that means, something like stood less or something like that. Okay. But you can also specify it in a different way with the so-called trailing requires clause. And this is maybe the first kind of syntactic sugar. Instead of type name or class, you just say sortable cont, which means cont should be sortable. Only a little bit of syntactic variations. Okay, this was sort. And this function templates requires from its argument that it is sortable. Let's continue. What can we do all? Okay, wait a second. One step back. When I now use stud list for my new defined stud sort algorithm, I would get an error message similar to this one, meaning concept random access iterator was not satisfied. When you invoke stud sort in C++ 11 or 14 or 17 with a stud list, you would get an error message about 50 lines. And the reason is quite simple. Stud list only has a bidirectional iterator, but stud sort requires a random access iterator. But you see, these are not 50 lines, only 2 lines, and explicitly saying to you, what is the reason? Okay. Only a short remark, which I will maybe mention once more. What is a concept? A concept is under the hood a constant expression, something which can be evaluated at compile time, and it's a predicate, something which evaluates to true or false. This is a concept. Okay, of course we can apply concepts to classes. Have a look here. I defined the class template my vector taking an object, whatever that means. Now, when I invoke my vector with an int, which is an object, this would be fine. When I invoke it with an int ref, this is not an object, therefore I would get an error message. I will show you concrete error messages in a few minutes, but I just want to show you the features which are possible with concepts. Okay, you can apply concepts to member function. The same class template such as before, but this time I say pushback. Meaning, in this case, for pushback, I require that the elements T are copyable to be usable in a member function pushback. So I can specify a concept on a member function of a class template. Okay, as I said it, boring because it just works. This is maybe not so boring. I just played with it. You can, of course, use it with fault expression in C++ 17. Okay, I defined here 3 function templates, all, any, and none. All checks if all arguments are true, any checks if any of the arguments is true, and none checks if none of the arguments evaluates to true. And you see, I don't use here type name or class, I use the concept arithmetic. To make it short, arithmetic is something such as it could be floating point or it could be integral. So if something is floating point or integral, it would work in my implementation. And here at the end, you see the application or the usage of this concept. I can say all true. It's a little bit too high for me. All true, such as here. It returns true, but all 5 true, 5.5 false returns false because false will evaluate to false, obviously. Okay, just works with fault expressions in C++ 17. You can even use more than one concept. Here you see the declaration, maybe the definition, okay, of the function template find. It requires that S is a sequence container. These are, by the way, official concepts we get. Maybe the wording will change a little bit. So S should be a sequence container and that the elements of S are equality comparable. Then it could be used in this function template. When you look at it, it looks a little bit like just documentation of your function. What can go inside or what not. But now it's more, it's a concept. Okay, you can overload on it. This is maybe the 5th version of advanced, I know, but this one is quite elegant. You know std advanced from the standard template library. It takes an iterator and a number n, and it puts this iterator n position further. Okay. I overloaded it here on 3 concepts. Input iterator, bidirectional iterator, or random access iterator. When I now invoke it with a list, which, as we know from before, only supports bidirectional iterator, then the most best fitting function will be chosen, which in this case the middle one, you see, bidirectional iterator. When I would use forward iterator, it would, forward list, it would use the input iterator. When I would invoke it with a vector or something like that, it would use this implementation. Why is this important? You know, I tell in my seminars, if you have an answer in C++, you cannot answer, you just always say performance. So the reason is why this is performance, it's performance. That's quite easy in C++. Okay, you can specialize on concepts. You see, boring, it just works. I have the primary or general class template. You see it, type name T. And I specialize, make a partial specialization on object, which means when I invoke it on int, this partial specialization would be chosen. When I invoke it with int ref, this, the general version or the primary class template would be chosen. Okay, it just works. Now we are done with the boring stuff. Now I come to the more interesting stuff. Okay. First of all, I want to make a short detour. What is the standard template library from a bird's eye perspective? We have generic containers, which can be manipulated by generic algorithms. Fine, all is generic, it just works. But sometimes you want to apply or use std sort, but sometimes you don't want to use the default ordering, which means lexicographically for strings. Maybe you want to sort strings based case insensitive, or you want to sort them based on their length. So there's an additional possibility to provide something callable, which gives you the predicate. Fine. But now we had an issue in C++11. We had generic containers, generic algorithm, and type-based lambdas. This was a conceptual break. Okay, no issue. In C++, this problem was solved. With in C++14, this problem was solved. With C++14, we got generic lambdas. You see, to make it clear, there's here an auto, which means this is a generic lambda. Fine, solved. We solved the first issue, but we created, from my perspective, an additional, maybe bigger issue. Which one? I often have a discussion in my seminars. If not, you can participate. Sorry. The issue is, what is a generic lambda? Of course, it's generic. It's a function template. We invented a new syntax for writing function templates. There's an exception to a rule. And if I want to explain something, I need rules, not exceptions. This was terrible from my perspective. Why? The people in my seminars now ask me, why can I not use auto in a function declaration? It becomes a function template. This is the next reaction you have to say, no, it's not possible. This is an exception. And this exception is gone with C++20, which is, from my perspective, totally fine, because I want to explain rules, not exceptions. Okay, do you see? This generic lambda is conceptually something similar to that. I know it's under the hood something different, but anyway. Okay. Now the syntax becomes a little bit more unified. What do I mean? Now we talk about placeholders. We have constraints and we have unconstrained placeholders. What is an unconstrained placeholder? You know it, auto. What is a constrained placeholder? A concept. And this is quite nice. So we talk now about placeholders. And let me show you something. Here's a simple example. It's not necessary to do it because the concept integral is already defined, but I did it only to show it to you. This is the concept integral. You see, under the hood, I used the function is integral from the type traits library, which we have since C++11. And this is my predicate, which will be checked or will be used by the concept. And you see, here I use my concept in GCD. And when I invoke it now here with two doubles, it says something like, let me think about it, constraint not satisfied. To be honest, this is not the error message of the draft concepts implementation, but of the concept CS, which we have since 26 or something like that. But anyway, you see, I got a quite nice error message. And my point was, I only want to show it to you because I want to use now these concepts. And here's the simple rule you have to follow, to keep in mind. In each place in which you can use auto, you can now use a concept. In each place in which you can use an unconstrained placeholder, you can now use a constrained placeholder. This is a simple rule. Let me show you a few examples. Okay, you see here, integral auto. This means this function returns something which behaves such as an integral. Okay, here, instead of auto, I say integral auto, which means E must support the concept of integral. Of course, you know what this means under the hood. It must be something in between bool and long int. Okay, I can use it for a bool, I can use it for an integral, and here only the old syntax. And it looks quite, what should I say? It just works, looks quite nice. So in each place you could use auto, means now you can use a constraint placeholder, which is a concept. And this is nice for me, really nice. And now to the slide I like most. I hope so. No, this one not. You see, it just worked. This is also not, now we come to syntactic sugar. Okay, I assume all of you know what syntactic sugar means. Syntactic sugar just means there's no new way to express something, but now it's a little bit easier to do. It's just a little bit sweeter. And this is totally important for software development. If you don't believe me, maybe C++ is syntactic sugar for assembler. So, I want to make my point. So it's important. Okay. Here I used the concept integral. You see, here the requires clause, which you know. Okay, it's simple. Here I used it with this a little bit abbreviated syntax instead of type name or class. And here, this is the stuff I'm totally interested about. This is the so-called abbreviated function templates syntax. This means I just define a function using not concrete types, but constrained placeholder concepts. And this function becomes immediately a function template, only accepting values which supports which supports this concept. This is a new way to define function templates without sharp brackets, you see? And this is the question I often have in my seminars. Why can I not do this? In particular, it's also possible to use auto now. In the for type parameter, just use auto. This is conceptually something similar, such as a function template or with unconstrained placeholders. It just works, and now defining templates is just a piece of cake. Okay. And boring, it just works. It's a GCC 6. What else compiler, but it works. Okay. A small detour because there's a little change. There was a little change in the semantic of concepts between concepts TS, taking specialization, and concepts draft. This is stuff we get now. The change was, now, let me show it to you, integral, the type of A could be different from the type of B. They have not to be the same. It just both have to support the concept integral, and you know what it means. This was first, in the first iteration, they should have the same time, but now they can be different. The same holds for auto here. The types of A and B could be different. Okay. A small detour because this is often a question I have after presentation. This was a change from the TS to the draft implementation of concepts. Okay. What can you do? Boring. Just overload on concepts. You see, I have a concept which I overloaded on auto, meaning on an unconstrained placeholder. I have a function overload which I overloaded on a constrained placeholder, on a concept. And I have a concrete function which I overloaded on long. When I now invoke it, as ever, the best fitting function would be chosen. This means in case of, go further. In case of double, this one would work, this one not. Okay, I go with this general case. In case of an int, I go with integral auto. In case of a long int, I go with long int. So you can overload also on concepts. This slide is red. Why? Because this is not part of the draft standard. This is part only of technical specification. Only I want to show it to you to make my talk complete. There was the idea of introducing or of a kind of template introduction. Instead of saying template integral t, you just could define integral t. This was a discussion. There was one restriction which puzzled me a little bit. This worked only for concept this t, but not for unconstrained placeholders. This would, in my perspective, also be an exception of a rule, which I don't like. Okay. I don't know if you get this syntax with C++23, but anyway, once more, this would be a way, you see, I said would be a way to define a generic function template only accepting types, values of type integral or supported concept integral. This would be the way to define it, use it for function template. This would be the way to use it for class template. And of course, which makes what I don't like, instead of integral, you could not say auto. This was even the TS specification not allowed. But what I don't like about these features, it is quite easy to overcome this restriction because you can just define a concept which always evaluates to true. So what's the difference? Now I could use it, which was crazy for me, to be honest. Okay, but you see, red slide, because we will not get it with 23. If I make any mistake, please feel free to interrupt me. Okay, and I just used it, so, but this is not so interesting. Oh, I was really, really fast. But anyway, define your concepts. Of course, you can define your concepts, but you should not do it. Depending modular spelling, we got a lot of concepts. So, for example, we have core language concepts, such as same, derived from, convertible to, common integral. You see, I defined it, but it would not be necessary to do it. Signed integral, unsigned, assignable, swappable. Okay, you can imagine what that means. We have comparison concepts such as equality, comparable. We have this object concepts. Okay, is this type destructible, constructible, move constructible, copyable, movable, copyable? Semiregular, regular, I will come to these concepts because I want to implement them, only to show it to you, but it would not be necessary. And of course, we have concepts just as callable, regular callable. Is this function a predicate, returns it true or false, or something like that? These are concepts we have. Okay, modular spelling, you see? I'm a fan, oh, I should not say it. I sometimes program in Python and I'm used to camel cases, but sorry. Okay, here's a little bit of variation. You see, on the left, you see the direct definition of a concept with the original syntax from the technical specification. On the right, you see the new syntax, which is a little bit more concise. Instead of bool, I say here nothing. This looks a little bit like a function declaration, but here you see concept integral. This is my concept from before. This is quite an easy concept, but yeah.
We did change the spelling in Cologne.
Really?
Yeah.
Which one? What is?
All of the camel case concepts were renamed to regular.
I know it. This was the reason, you see. Modular spelling.
So in the draft C++ 20 standard, it doesn't look like that.
Sorry, I know that you changed it, but I actually don't know the names. Sorry. Okay. Maybe this was a misunderstanding. He's totally right, I know it. We love underscores. No, consistency is also a virtue. So anyway. Okay, but you see this was the old syntax from the concept CS, and on the right you see the new syntax, the draft syntax. Okay, this is a kind of a direct definition. This is easy, but there's also a definition which uses internally or requires expression. On the left, you see the old version, on the right, the new version. All my examples are made with the left version, but I show you the right version. Anyway, you see, instead the bool is missing. It also looked kind of a function declaration, kind of, or definition, sorry. But here I say concept equal, and then I say what is required. So I define the concept equal. Of course, you know what equal means. It requires for two different types of E that, let's say, should be of the same type. Let's say support A equal and unequal, and that this function should return a bool. This is the concept which I explained. And if this holds, I can use a type when I use this concept equal. And you will see it, or use a value. You will see it here. Here's the first use case. I defined the function template R equal, and you see A equal auto. So I require that A and B support the concept equal. Then only for demonstration purposes, I defined a class without equal because I deleted equal, and without unequal because I deleted unequal, only to make my point. Then I invoke this R equal with ints, which of course support equal and inequality. This is easy. But you see there's something is commented out, and I show you what would happen when I invoke it without equal and with an instance of the type without unequal. Okay, at the top you see the good case, at the bottom you see the bad case, in which I use this without equal and without unequal. And when you read carefully, you see identity would be ill-formed. Unequal would be ill-formed. This is the message I got with the concept TS when I used these concepts, and my types didn't support these concepts. Okay, this was easy. Now one step back to Haskell. Okay, this is the way, only to show the similarity, this is the way the type class equality or equal is defined in Haskell. It means it has to support the equal operation. A and A, both arguments, have to be of the same type, and it should return a bool. And the same for inequality, you see? And now if you compare it to the right, this is the concept equal defined in C++. It looks quite similar. And what is nice from my perspective is the syntax is quite concise. So it's not so verbose. You see, concept equal requires TATB. It has to support the operation A equal to B, and the return type must be a bool, and the same goes for unequal. So it looks quite similar. You will see in a few seconds why I showed you this page. Okay, once back, this is Haskell type classes hierarchy. Then I was curious, could I implement something similar, such as here, with concepts? This is, of course, Haskell. I was just curious. And what I explicitly want to do, I want to build this part of this type classes hierarchy in C++. Is it possible? Of course you know it. If not, I would not show it to you. Here is Haskell's type class ordering. You see, only to see a little bit syntax. To support ordering, A has to support equality and these 6 additional operations. Of course, smaller equal, greater equal. And compare and max, I will ignore them. But you see, this is the way Haskell would say, when you support ordering, you have all this to support equality and this additional 6 methods. How would it look like in C++? And here's the solution C++. At the left, you see equal from before, the concept equal. On the right, I said concept ordering requires that E supports the concept equal and logical and the rest. So smaller equal, smaller, greater equal, and all function calls must return bool. So for me, it's extremely elegant. Let me try it out if it works. Here, have a look. As before, the function R equal, you know it, but here gets smaller, which requires from A and B that both support the concept ordering. And of course, what goes back should also support ordering, which is trivial in this case. Okay, now let me use it. You see, with int, here and here I can use the function R equal and get smaller, because both ints support, of course, all operations. But now I use something which gives a hint because of the name. It's called unordered set, which of course don't support ordering. When I invoke R equal, it would work. This would go. But when I invoke it, it gets smaller, it would not work because an unordered set has no idea of ordering. And this is what I get. The first case is a good case. And the second case is in which I used this unordered set. And here you can see it, read it quite good. The required expression would be ill-formed. So this is the entire error message. And the reason was you cannot order an unordered set, of course. Now to my last concept I want to define. In C++, we have, how should I say it? I should not say concept. We have the idea of a regular and semi-regular type based on Alexander Stepanov, as far as I know. What is a regular type? I will make it extremely short. It's a type which behaves quite smoothly in the C++ ecosystem. It's good to handle with this type. What should a type support which we call regular? First of all, the big six. Hey, sorry, six. Big six. Default constructor, destructor, copy, move, assignment, copy, move, constructor, the big six. And additionally, swappable and equality comparable. Then we call this type in regular type. When I subtract from this regular type, equality comparable, I got a semi-regular type. Now I want to define a concept which I call regular and semi-regular. This was just a challenge I had. Could I do it? Okay, let me start. This would be extremely easy. I just used functions from the type traits is default constructible, is copy constructible, copy assignable, move constructible, move assignable, destructible. These are the big six. I can just use functions of the type traits library to ask, are all of these big six special methods supported? I can even ask, is swappable? Okay, this would be fine. And what you see here, for intref, I got the answer false, of course. You cannot default construct a reference. Okay, this would be easy. Semi-regular is a piece of cake. I have just to make a concept and put a few logical ends in between. Okay, but what about regular? Regular is a little bit more complicated because there's no is, did I call it? Is equality comparable or something like that. There's no type traits asking, which allows you to ask a type, do you support equality comparable? So I have to build it by myself. I used it with a so-called detection idiom. It looks a little bit crazy, but it works. By the way, this is a C++, as far as not part of C++ 20. Anyway, if I make a mistake, say something. I'm relatively sure because yesterday I created the standard once more and this is not available. I think it's part of C++ 23. This is called a detection idiom. And the key idea is you can ask a type if it supports a specific, in this case, operation or method. And you see, I ask if T supports equality. And here I use it to create a type traits. So to ask at compile time, does my support equal, my type support equal? Because this was the missing part I needed to define regular. Okay, now I use it, you see? It's just a little bit to write. I create is semi-regular. I just combined all type traits. And then I created, wait a second, I'm a little bit, is regular, is semi-regular, I'm a little bit irritated. This is semi-regular. Okay. Yeah, you see, I'm unable to read. This is called semi-regular, this is called regular, so I'm fine. The slides are fine. My eyes are bad. Once more, is semiregular. Here I combine all the type traits which are necessary to answer the question, is it semiregular? And here I use this from above, is semiregular, combined with my type trait. And now I can detect at compile time, is it regular, is it semiregular? And here I use it. Now you see, here I use it, is semiregular. This is kind of similar to type traits. And here I just defined two concepts. Regular is regular, semiregular is semiregular. Now I'm done. Now I can check, is a type regular or semiregular at compile time. Now I have a new concept, which would not be necessary because we already have a concept regular in C++20. But anyway, this is a good way, by the way, this is a good idea. Never try to invent a wheel once more. Use the concepts which are available. Okay, you see, I was really fast, 45 minutes, maybe too fast. Okay, this was the overview. This is the overview to my talk, and now to the final question. Your opinion may vary, but this is my opinion. You see, is it an evolution or it's a revolution? Here are my arguments. What speaks for evolution? Auto, of course, speaks for evolution. We have auto since C++11, at least with the semantic, you know. And now we have unconstrained placeholders. Maybe now we have constrained placeholders. So it's quite an evolution. Then, as I mentioned it, since C++14, we can use auto in generic lambdas, or we can use auto in lambdas, which makes them generic lambdas. So it's also not so new. It was only a kind of evolution. This is the part which speaks for the evolution. But what speaks for the revolution? Template requirements are the first time verified by the compiler. This is new. Okay. The declaration definition of template radically will improve. Why? You see, just use a function, use a concept, or use an auto, and it becomes a function template, with or without constraints. This is also new. Now we can define concept without sharp brackets. And this is my main argument. Concepts define semantic categories and not syntactic constraints. What does that mean? Now I can define a concept such as equal, ordering, or what else, or some mathematical concepts, because I looked at you, so sorry. But the point is, now we can specify our arguments based on semantic categories and not on syntactic requirements, such as, does this type support a has ABC function or something like that? This would be a syntactic requirement. We think about semantic categories, which we of course know from math. I don't know what your opinion is. Of course I have one, and now I'm done. Let me continue. Let me add a few sentences. If you want to learn German, you should use the first link. This was a joke, sorry. If not, I will start in 2 weeks to write about this stuff in detail, about maybe 5 posts about concepts, because my blog is currently about C++20. Now I started to write about C++20, and I will continue to write about C++20. And my next feature, which I will show in detail, are, of course, concepts. Okay, but now I'm done. As I see, I was too fast. I don't know why, but anyway. Okay, any questions so far? I think you should go with the mic if necessary. Oh.
This was dangerous.
Hey, thanks for the talk. So you mentioned that you can overload with concepts, and it will pick the best or most specific concept that is possible. How does the compiler actually know which concept is the best or the most specific?
Sorry? The most restrained. We have to believe him. Yes. He says yes, so what should I add?
I know it from Andrew Sutton.
Okay, this is the final proof. Good, thanks for the answer.
More questions?
Boris, okay.
Let's start over there.
I don't know.
Thank you, Rainer, for your talk. When you defined your own concepts with requires, and you specified all the operations that should be possible, this was basically another syntax for decal type, right? You were checking whether you can compare A and B, and whether that comparison will be a Boolean value. Is this a list of what we could express with decal type?
To be honest, Boris, I don't understand your question. I know what decal type is, I know what you said, but can someone kick in?
I will just come to you after the talk.
Maybe. If not, someone wants to kick in, I'm totally happy. No.
I will come to you
Not
after
even
the
you?
talk.
I have a question.
As long as you have to answer this question. No question. Sorry, Boris.
Answers. You want answers?
Sorry.
My question is, do you believe this concept is a groundbreaker or I don't need the mic, thank you.
You need it.
So, do you believe it's a groundbreaker or a game changer? Thank you very much.
This is
Thank
my
you for
point.
your talk.
But you saw, for me it's a revolution, so what should I add? Why? Because we now have a new way to express generic code. And I started with this talk with one wrong race, specific, generic. Both ways have big issues, such as conversion and this stuff, such as terrible error messages, big issues. And now we have something in between with semantic, which is for me something totally new. What I like about these concepts, ideas, I studied math. I could teach math now in my seminars. What is a monoid? This is total new dimension for me. It puts us on another level, on a type level, on a conceptual level. Sorry. For me, it's groundbreaking.
Any future for use of enable if against concepts?
But enable if is for me something different because it's about conditional compilation. A decision which you make, should I use this one or this stuff? So it's a little bit different story. It's kind of similar because it works quite early, compilation or maybe time or before, but it's anyway something different. Or any remarks here? Now, David.
Yeah, answering that question particularly, if you look up if const expr, if const expr, that should replace enable if. I don't think concepts will, unless we have if concepts, but then we'd have to get past the.
Do you ask for const expr if or enable if? Sorry, I answered const expr if. Sorry.
That's
Thanks.
the thing.
In our code, when do you think we should start to define a concept? So what do you think that if it is really here a semantic problem, if you have something like some keywords to say, okay, in this moment, I tried also to use concept, and for me it was I just make my code complicated. So maybe I'm totally wrong, or
I didn't mention it, but if you read CPP reference and you read something like such as sort, the types or names of the arguments are kind of strange. Or if you read lock, and it requires that the argument is lockable. What does that mean? This is a concept. This means was before only a hint for the reader what can go inside now becomes something more important, something which is a concept, which will be checked by the compiler. You can also look at concept as only a kind of what was in former times only a hint for the reader, what can be used here, is now something which has a type-based contract. I don't know how to say it differently. The point is, I would never suggest to you to invent your own concepts in the first place. Just use the existing one, use into CPP reference, use at, for example, read stood sort. There's maybe an argument which is called bind it or random it, which stands for random access iterator. So we already use it, but they had no influence on the compile time. So for me, it's quite natural. What we used as a hint to give the reader or user what should go inside, it's now something more, meaning a concept. So we already use them, but now they are more than just a hint for the reader.
Thank you for the talk.
Yeah.
The question is, so given that we have function that with two arguments, and both of them defined as equal comparable, and then we less compared inside this function, will compiler already complain about it? Or it will complain once the function is instantiated?
Once more, you have a function which requires what from the arguments?
Two arguments equally comparable.
Equally comparable. And you do something like smaller in the body.
Yes, right.
Okay, and the point is?
The question is...
No, there will not be a concept check. It is the question how you invoke this stuff. And then it will break or not, depending which arguments you use. But anyway, you define something terrible.
Yeah, that's certainly true. But this is kind of a difference between Haskell type classes.
Yeah, in Haskell you know it. I should not talk about Haskell because sometimes Andre says something about it.
Yeah, maybe it's worth mentioning
that. The point is, with Haskell you have to implement or to fulfill a type class. You have to say, I implement this type class. I have to support these methods to be comparable. With C++, it's the other way around. You invoke it and then you get a nice error message.
Okay.
So it's totally different. So there are a few differences between Haskell and type classes and C++ concepts. First of all, we don't implement a type class, we just use the concept. Second, it's a compile time story instead of a runtime story. And there was an additional point which I forget, but anyway.
Yes, thank you.
And of course, there's one difference. In C++, you can also define concepts on non-types. I never saw it. I only used it for types such as int. A non-typed is maybe a 5 in value. It is technically possible. I never saw it. So, but anyway, so it's more than on types. It's also on non-types.
Okay, I see. Yeah, thank you.
Maybe a slightly naive question, but what's the recommended way of mixing and matching or combining several concepts? Is there some syntax for combining several concepts on the same type? Or should one make always the like a composite concept that combines several?
What do you mean by compile?
If I want the type to satisfy not one but several concepts, should I make a composite concept or is there
okay, to be honest, I don't know. There are many ways to express it. You can use logical AND, logical OR, something like that to express something. You can use one concept to refine it with another concept. I think this is more a matter of software quality, or I don't know how you write good code. I don't know it. My concepts are extremely easy to read. If you want to read more sophisticated concepts, look into the ranges library of Eric Niebler, for example, or look into the new C++ 20 standard or the upcoming 20 standard. Then you see what's happening under the hood. Mine were extremely simple.
Thanks.
Hi. In your, you gave an example of integral, and your GCD function takes two integral arguments, and you said that the standard allows the two types to be different.
For example, short and int or something like that.
Correct. But if you passed two arguments of two integral types, which actually you couldn't do the % operator on both of them,
the modular operator, you mean?
Yeah, the modular operator.
Okay.
So therefore, like, you might have, I don't know,
then you are as good as before.
Okay, so
you will get a template instantiation where we love, because you see.
Okay, right. But that's the only time you'll get a horrible error message now.
Maybe this is, I see no difference to before. You just check, I should not say contract, but you just check the declaration of this function template, if it works. You try it out and you know, template instantiation is in this regard eager. It tries to instantiate it and sometimes it fails with these horrible error messages.
Okay, thank you.
More questions?
Perfect.
All right.
1 minute is left.